coli cell, a plasmid, containing the gene encoding the protein of interest, we do this a lot in Chem 164. So for example, my wife studies apolipoprotein A1, which we'll get to in the second semester. It's a protein that's involved in cholesterol transport. It's a human protein, all right? The old way that she would purify it, she would actually go and get expired blood serum from blood banks. So, you donate blood so that, and then blood banks have the blood. Well, it's only good for so long. So when it's expired, she would go get the expired bag, and then she would basically purify this protein out of there. But there's limitations. It's a relatively complex protocol. There's limitations to the amount that you can ultimately get. So now what she's done is basically gotten E. coli strains that contain a plasmid that have the human gene for this apolipoprotein A1. But basically is tell the E. coli cells to make a whole bunch of that protein. And these E. coli cells are all specially engineered to be protein production factories. And so now they accumulate tons of that. And we've used that for projects in Chem 164 for the last half dozen years or so, and it works really nice. So you basically engineer this and then induce protein expression. So now your E. coli cell is full of your protein of interest. And again, the example that we talked about on Monday was this is the original breakthrough of the biotechnology industry was to take the gene for human insulin and put it into an E. coli cell, generate the protein of interest, and then purify it out that. And then that basically enabled the use of actual human insulin versus pig insulin or cow insulin. And the other thing that this does is once you get there with the gene, is if you want to tweak the sequence a little bit, you know what, I wonder what happens if I change this amino acid to another amino acid. You can engineer your gene to encode slightly different amino acid sequences. And so you can get different variants, different genetic variants, and you can either study those or, like in the case of insulin production, there are different variants that have slightly different pharmacokinetic properties so that they'll last longer or more short-acting and that sort of thing. So, and just to kind of, so typical kind of these E. coli cells are known as host cells. Typical hosts, I gave the example of E. coli, that's one, but also yeast, mammalian cells. Particularly good for producing monoclonal antibodies, which a lot of the new drugs are actually monoclonal antibodies. And so this is basically, or this is the basis of the biotechnology industry. So if you're driving down I-80 towards the Bay Area, and you're going through Vacaville, right before you get into Vacaville, you look over the right, and there's one of the world's largest protein production facilities. And what it is there's great big huge fermenters in there. They're growing mammalian cells. Those mammalian cells have been engineered to produce pharmaceutical proteins. And then they have rooms 2 or 3 times the size of this room that's full of protein purification equipment that goes and purifies these proteins. They produce things like Sept, which is an anti-breast cancer drug. All right, and so basically the whole biotechnology industry, multi-billion-dollar industry, is all about creating an enriched source for protein purification. All right, so next on, now you have your source, you still, even if you've got a whole great ton of your protein in there, there's still all the E. coli proteins in here. So we got to separate out the protein of interest from all your E. coli proteins. So there's, again, a series of different methods based on different characteristics of the protein. Let's first talk about ion exchange chromatography. And the fundamental idea is, here's that we have a column. In the column is a stationary phase, and that stationary phase has a series of charges. Now, most proteins at neutral pH